So, welcome students to the next class of nonlinear optics and its application. So, we have already studied in future classes the basic optics or basic linear optics. We will continue that. So, in the previous classes we were going to learn we were studying that how the electromagnetic wave is propagating inside a anisotropic medium, and then we will understand how for different orientation of the k vector, what is the direction of k vector and the associated s vector, that means the Poynting vector. So, we will extend this and try to find out different kind of solution under the launching of different direction of the light. So, today we will going to learn in the basic optics. So, EM wave propagating in an anisotropic medium, and then we will going to learn the ordinary and extraordinary ray. What is the meaning of ordinary and extraordinary ray? We will going to learn that, and then the index surface. What is index surface? We will study. So, these are the three basic topics that we will going to cover in this particular class. Okay. So, this is the very old equation. We have used this equation earlier. Since this equation is very important, so I thought again I should give you the picture what is going on. So, if the k vector is launched in a particular direction where the direction cosines are rho x, rho y, rho z given in the green line here, then from the Maxwell's equation we have the relationship between E and rho and k are like this. So, this equation was already derived in the previous class. So, I am not going to derive it once again, but this is the basic equation that we have, and we need to find out the solution of E x, E y and E z with the condition that the rho x, rho y is given. So, that was the equation we used earlier. So, now in the next case what happened, that we put some kind of condition. So, what kind of condition we put? Just we put the value of rho x, rho y, rho z. In the first problem we put rho x equal to 0, rho y equal to 0 and rho z equal to 1. That means that the electric field is launched in z direction. So, this was the direction along which the electric field was launched. So, k vector is along this direction, and try to find out what are the solutions, and we figure out there are solution in x and y direction. These are the x polarized solution and y polarized solution. We call it the polarized state and eigenstate. So, that means this polarized state will remain conserved. We also find that. Next, in the next part we try to find out what happened if the k vector is launched with an angle phi with the z axis. Whatever the axis is there is x, y, z. So, with the z axis it is making an angle phi, and also k vector k is in x z plane. It is in x z plane. It is in x z plane. If that is the case, then rho x, rho y, rho z will have simply the form like this. So, rho x will be sin phi, rho y will be 0 and rho z will be cos phi as shown here. So, if rho x, rho y, rho z is given, then we can use these things into our old equation as shown here. This is also an old slide, this is not a new slide, but I want to recap once again what is happening here. And then if you put rho x, rho y, rho z into the equation, these things into the equation, this equation will be converted to an equation like this, and you find that there are three equations related to E x, E z, E y and E z. One equation here is containing only E x term. That means that one solution we can take, which is some sort of trivial solution here, that E x equal to 0, E y, E z equal to 0 and E y is not equal to 0. That means, in order to satisfy this set of equation for a given rho x, rho y, rho z, I try to find out the solution of Ex, Ey and Ez. Here Ex and Ez is considered to be 0. If that is the case, this equation and this equation satisfy naturally, or these are the trivial solution. If you put Ex and Ez 0, both the equation will satisfy. And if Ey not equal to 0, from this equation we can say that my refractive index n should be equal to root over of k of y. That means my refractive index along y direction is root over of ky and Ey is not equal to 0. That means Ey is along y direction, that is a non-zero component, all the other components are 0, and if I launch the k vector in one particular direction, which is making an angle phi with respect to z axis, and it is in x and z axis, then I can have a solution with Ey not equal to 0, and the corresponding refractive index is also given in this equation. This is we have discussed earlier. So, these are the solution 1 as I mentioned in the earlier slide, that in solution 1 we find that even if I launch k vector in one direction which is making an angle phi, and if it is in x and z plane, then we have a solution of E which is moving without any kind of change, and it will be polarized along y direction. And these are the solutions that Ez is not equal, Ez is 0, Ey is 0, but Ex is not equal to 0. So, E is perpendicular to xz plane. So, that means E will be perpendicular to k as well. So, in anisotropic system, mind it, this equation is strictly valid for anisotropic system where E and D is not supposed to be parallel, but we have even in anisotropic system we can have a solution where E and D can be parallel if I launch k vector in xz plane with an angle phi, and one trivial solution is this. Well, let us try to find out what are the other solutions one can have, and this is the solution 2, and the solution 2 is interesting because in solution 2 what happened, that I launch the k vector as usual in a direction which is making an angle phi with z axis, but here we are taking Ex and Ez not equal to 0, which in the previous case was 0. Here we consider this is not equal to 0, but Ey is 0. That means essentially the E vector is in x and z plane. So, I put E vector in x and z plane. If that is the case, xz plane is the plane of this paper or slide whatever, and in this particular plane if the E vector is there, then the solutions what we have was this. So, now this is 2 equation. So, from this 2 equation we can solve, that is one method, 2 equation 2 variables are there. So, we can solve that. If the phi is given to you, then you can solve, but we will try to do something different here and try to find out some condition. What kind of condition we try to find out, let us see. So, if in the solution 2 Ex and Ez is 0, then as in the previous slide we find we have 2 solutions in our hand, and that is this 2 equation in our hand, that is this. So, considering that we are now for the time being not bothering about to find out the value of Ex and Ez, rather try to find out what should be the condition for non-trivial solution. So, here for non-trivial solution means for non-zero value of Ex and Ez, what we should have, what is the condition, and we know that this is a matrix form, and this matrix form if I have, so if I write this matrix form as say A11 Ex plus A12 Ez is equal to 0, and then I can write A21 Ex plus A22 22 E z equal to 0. So, this is a matrix form kind of thing. So, I can write the entire thing as A 11, A 12, A 21 and A 22 multiplied by E x E z equal to 0. So, that is the equation. We know that if we have this kind of form, then what happened, that for non-trivial solution Ex equal to 0, Ez equal to 0 is also a solution of this kind of equation, but this is a trivial solution because I am putting both Ex and Ez is equal to 0. But for non-trivial solution, what happened, the determinant of these things has to be 0, then only have a non-zero value of Ex and Ez. So, in this case, so I have A11 is this quantity, this is my A11, this quantity is A12, this quantity is A21 and this quantity is A22. So, now if I put all this A11, A22, A21 and all this value here, then I can have the matrix form, and this is the matrix form of this A11, A2, A12, A21, A22, and the determinant of these things is 0. Once we have the determinant of this quantity 0, we will have an equation out of that. So, this equation, so let me explain that. So, this is my equation here. So, determinant equal to 0. So, determinant, if I now decompose this determinant, then this cross product and this cross product with a negative sign will be 0, that we know. And then if I simplify these things multiplied by these things, what we have. So, kz kx divided by into the power 4 this, then kz n square cos theta cos square theta and 1 kz kx n square sin square theta. So, if I take 1 by n square common, then we have kx sin square theta and kz cos square theta this. So, once I have this term, then another term will be here. So, these are the first. So, 1, 2, 3, 4 terms are there. From this 4 term, if I multiply, then we will have 1 term, 2 term, 3 term and 4 term. So, 3 term is written here. So, 4 term will be plus cos square phi sin square phi. So, this term will be cancel out with this additional cos square phi sin square phi. So, it will be cancel out. So, eventually we will have one equation like this. From here we have a very important equation, and we will going to learn about this important equation, and that is why it is in the bracket. So, 1 by n square is equal to cos square phi k x plus sin square phi k z. Why it is important? Because this equation suggests that the value of refractive index for non-trivial solution of kx and ky, obviously kz. So, from that equation leads to one very important equation, and this equation suggests that 1 by n square is equal to cos square phi divided by kx plus sin square phi divided by kz. Very easily one can derive from this determinant to this equation. So, all the steps are given. So, I will like to I will be happy if the students who are taking this course can do that by their own hand, then they will understand how this, but the calculation is very simple, but all the steps are done here. So, nothing very new here. So, 1 by n square is cos square phi kx plus sin square phi kz, and this suggests that this now whatever the n I am talking about is a function of phi. That is a very important, because in the right hand side we have phi, and this kx and kz are constant term. That means what is phi? What is phi? If you remember that, the phi is nothing but the angle that is making by the k vector with z axis. So, this was the phi. If I go back to the previous slide, or if you notice carefully, my k vector was in xz plane and it is making an angle phi with the z axis. If it is making an angle phi, then this ray will experience a refractive index. Obviously, this refractive index will be not very simple refractive index, it will be a complicated kind of refractive index, and here we find an expression of that. Again we will come back to this point, but you should appreciate that this refractive index, value of this refractive index will be a now function of phi. That means this ray and whatever the ray is here, suppose I am launching the k vector in this direction having a new phi, say phi 1 or phi dash, then from this equation I can say that this refractive index is now changed, which is very important thing, that now my refractive index is direction dependent. And in anisotropic system, this is one of the important thing, that if you go in different direction, different physical property will be there. So, physical property is direction dependent, and physical property means here is nothing but the refractive index. So, if you go in different direction, you will have your different kind of refractive index. Okay. So what so far we have an expression like this, and if I now simplify these things slightly, that making a kx, because I need to find out what is the condition. So, in order to find out the condition or the relationship between Ex and Ey, so what we will do, that using these things I will have one expression like this. If you look carefully, these things is same which is here. So, I just replace, now what I will do, I just replace these things here with this term and then find out what is going on. Okay, go back to our slides, and this is the next slide. So, in the next slide what happened, as I mentioned, I just replace these things to whatever the value we had there, and if I replace this, so this was the equation earlier. So, this is the value we derive, and these were the two solutions. From here I have the determinant form. So, determinant form, this term was there. So, in these two equations what we are doing, I am just replacing this quantity here with this one, sin square phi kz kx. If I do, then I will have Ex, which is this one is Ex, then it is multiplied by this quantity sin square phi, this you can see that this is multiplied, that will be equal to this, because I am replacing these things, and these things is nothing but minus of these things from this equation, because if it goes this side there will be a negative sign. So, this, and from here we have a relationship between Ex kz and kz kx, and this relationship suggests that Ez kz divided by Ex kx is equal to minus of tan phi. So, try to find out what is going on. This is my k vector which is making an angle phi here, and then my E vector, because it is a non-trivial solution, Ex and Ez was equal to 0, but Ey was not equal to 0, sorry, Ey is 0, but this things was not equal to 0. That means, my E vector is in, this is my z direction, x direction, somewhere here in xz plane, this was my E vector. Now, these two components are related to this angle phi. So, the component, I know that this is, if I make these two component, so this component is the Ez component and this component will be the Ex component. So, Ez and Ex component will be related to tan phi, and if I do that, my Ez Ex will be minus of kx kz then tan of phi. What is the meaning of that? That means, this is how much? If I say this angle E z, so if this angle say okay, if this angle is say theta, then E x is nothing but E 0 cos theta and E z will be E 0 of sin theta, and since this is a negative side, I can put a negative value here. If I make a ratio out of that, then E z E x will be minus of tan theta. So, that means tan theta, which is the angle making by E x E with x, is equal to tan of phi multiplied by k x divided by k z. So, k x k divided by k z, if this term is equal to 1, then what happened? Tan phi was equal to theta, and that eventually means that k vector and E vector are perpendicular to each other. That means, for anisotropic for isotropic system, they are perpendicular to each other, and we know that. But here this quantity, since k x and k z are not equal to each other, then that means some multiplicating factor are there, and that means theta and phi are not equal. So, that means what happened, that the angle between these two things are not 90 degree. So, there will be some angle difference. Okay, that is the physical thing that we can say. So, again we derive the entire thing here, and you can understand now clearly whatever we have done in the previous slides. So, these were our equations, and we find this is the thing, and now we can modify this equation, because in principal axis system these are the relationship between D and E. So, that means if I do, then we find that E z k z is nothing but d z, and E x k x is nothing but d x. So, we can replace these things, and here now we will find that d z divided by d x is equal to tan phi. So, now this is nothing but, if I am making an angle say in the like the previous way. So, this angle is say tan psi, if this angle was psi, and we find that this psi is equal to phi. If this psi and phi are same, and we can say that k and d are perpendicular to each other, because this angle and this angle is 90 degree, and this angle plus this angle is 90 degree. So, we will have a relationship between phi and psi, and this phi and psi are same, that means d and k are really perpendicular to each other. But for E vector it is a different story, and for E vector we find this ratio is present here, and because of this ratio what happened, that there is a different angle. So, here I say this is theta. So, from this figure I can say this is my theta. So, here this phi was equal to this psi was equal to phi, because d and k are perpendicular with this treatment, we can readily understand. But theta we can find, and this theta is nothing but whatever the angle we get, tan inverse of that. This is the old equation, the previous equation that we derive. So, tan theta is equal to k x k z tan phi. So, theta is equal to tan inverse of that thing. So, I have the value. So, that means if k x k z value and phi value is given to you, then you can have what is the value of theta. So, now the interesting thing, I want to find out the deviation between E and D. This deviation is nothing but the angle between S and K. That means, S vector, if you remember, is perpendicular to E vector. So, S and E, they are making their difference is delta. So, if delta is there, so delta is nothing but theta minus phi. So, this theta minus phi is called the walk off angle. So, walk off angle one can easily find out. So, that means if I launch an k vector one direction, so S vector will be in different direction. If somebody want to know that what should be the direction of S vector with respect to k vector, that means what is the angle between k vector and S vector, here in this treatment we call it delta. So, delta will be equal to this amount. So, kx kz is given, if kx kz is given to you and if phi is given to you, then you will find out what is the walk off angle between these two. Well, I think we are almost in the last part. So, let me give you the hint, some idea about what was the equation. You may remember this equation I have shown you earlier, that is a very important equation. In the next class again we will deal with that. So, this equation suggests that n is a function of phi. So, now in the uniaxial system what happened, that there is an axis called optics axis and it is normally considered along the z direction, where the velocity of two wave is same. That means, the refractive index is same along this direction, and the refractive index for ordinary and extraordinary wave are same, means ordinary wave refractive index is same in all the direction, but extraordinary wave is related to this refractive index, where it depends on the launching of the light. That means, if I launch a k vector in different direction, if the medium is anisotropic in nature, we have a refractive index structure shown in here, which is ellipse in nature. This is nothing but a structure of ellipse with respect to phi. So, this circle suggests the refractive index, and this refractive index is same in all the direction. So, this is corresponding to the refractive index for isotropic system. That means, there is no refractive index difference in all other directions. This is the same for all launching angles. But here if I launch an k vector with a particular angle, say phi, then what happened, that at this point, at this point, at this point, if I change my angle, you will find the refractive index is also changing. And when the phi is here, that means when the phi is pi by 2, according to this equation what happened, sin cos pi by 2 is 0, this term will cancel out. So, 1 divided by n square, if I write phi equal to pi by 2 at this point, what will be the refractive index of the system? Sin square phi by 2 is nothing but 1 and it will be kz. So, the refractive index will be kz, and kz is the refractive index of any. So, this refractive index will be the extraordinary refractive index here at that point. Now, if I reduce and go launch the electric field along this direction. So, k is along this direction, that means phi is equal to 0. So, what happened from this equation? So, let me erase whatever we have. So, what we are doing, we are launching the k along this direction, so that my phi is equal to 0. If my phi is equal to 0, if I put these things here in this equation, what happened, that phi is equal to 0 condition, 1 divided by n square, phi is equal to 0 in this condition, my general refractive index 0 means this quantity is not there, 1 divided by NO squared. So, refractive index will be equal to NO, and you can see that at that point the refractive index is NO. That means, along this direction the refractive index is same for O ray and E ray. That is why this ellipse just touches here, because the n value which is a function of phi will be coincide with the value of NO at that point, and if I now gradually changing the direction, then we find this value is my NO value and this value is my NE value. So, that means, in this direction the refractive index is completely different for two different rays. The ray which is following the ordinary refractive index is called O ray, the ray that is following the extraordinary refractive index, that means the refractive index that is depending on the direction is called the extraordinary ray. So, we will discuss in our next class. So, we will like to stop here. So far we learned that there are two kind of refractive index. In one direction we have one refractive index, in perpendicular direction this is a different kind of refractive index, and there is a mismatch between these two refractive index. So, this will help us to understanding few things in nonlinear optics. Why it is important we will going to learn in our future classes, but in anisotropic system it is interesting that we have two different kind of refractive index. One we call the ordinary refractive index, in another we call the extraordinary refractive index, and extraordinary refractive index is a function of direction. That means, it depends on in which direction I am launching the light. Based on the direction of the launching of our light, we have different refractive index. That is an interesting thing, and we will learn more in our next class what is refractive index, ellipsoid, and all these things, how these things look like in real picture we will going to learn. With this note, we will like to stop our class here. So, see you in the next class, and thank you for your attention.